This is MEG 224, Engineering Mechanics 2, Dynamics, Lecture 7, Planar Kinetics of a rigid body. Force, mass, and acceleration. Part A. And this can be found in Chapter 17 of Engineering Mechanics Dynamics by R.C. Hibler. The lecture objective. The objective of this lecture is to introduce the methods used to determine the mass moment of inertia of a body. Mass moment of inertia. In the lecture of statics, we had looked at moment of inertia. Now we're going to look at mass moment of inertia, because there we looked at area moment of inertia. So a body has a definite size and shape. Unlike a particle, an applied non-concurrent force system can cause the body to translate, to rotate, or to both rotate and translate. In statics, when you talk about statics, you're talking about the summation of all forces to be zero. That is the net force acting on an object will be zero. That is, an object will be stationary if net force acting on it is zero. But if the net force is not acting on it, the object will either translate or rotate. And the translation movement will be in the direction of the force. So the translational aspects of motion are governed by the equation of motion, which says that F is equal to ma. So the rotational aspect of the motion are caused by a moment, m, and are governed by the equation of motion of the form m is equal to I alpha, where I is the moment, is the mass moment of inertia, because we have area moment of inertia. And then by comparison, the moment of inertia is a measure of the resistance of a body to angular acceleration. In the same way, the mass is a measure of the body's resistance to linear acceleration. The moment of inertia is the integral of the second moment about an axis of all the elements of mass dm, which compose the body. So, for example, the body's moment of inertia about z axis in the figure is this figure now. This r is radius. We are looking at just a piece or a particle in the body, and it's called or is measured as the m. So the moment arm r is perpendicular to the distance from the vertical axis to the arbitrary element dm. Since the formulation involves r, the value of I is different for each axis about which it is computed. If you compute your I about x and y axis, they are the same, but about z axis, it's going to be different. So in the study of planar kinetics, the axis chosen for analysis generally passes through the body's mass center and is always perpendicular to the plane of motion. Here, the plane of motion is the XY plane, and then Z is the perpendicular axis to the plane of motion. So your moment of inertia will be about this axis. So if your motion, plane of motion is vertical, is planar and is vertical like this, then the axis of moment of inertia will be horizontal through the center. The moment of inertia about this axis will be denoted by IG, that is the moment of inertia through the mass center of the body. Since R is squared here in this equation, R is squared, the mass moment of inertia is always a positive quantity, because whether you have R plus R or positive R or negative R, R is I will always be positive, because R square will always be positive. So common units used for its measurement are kilogram for mass and then meter square for R square. If the body consists of material having a variable density, that is, the material is not homogeneous, then P will now be X, P of X, P of Y, and P of Z. And the elemental mass, the M, of the body can be expressed in terms of its density and volume. You know that density density is equal to mass over volume. So then mass will now be density times volume. Substituting the M into the first equation, so the body's moment of inertia is then computed using volume for integration. So I will now be integral R square rho dV within the limit of V, because the M is now rho dV. So in the special case of rho being constant, then rho can be taken out. So then we now integrate. The integration is then purely a function of the geometry, that is the geometry of the particle or of the body. So I will be equal to rho integral R square dV. When the volume element chosen for integration has infinitesimal dimensions in all the three directions, figure A, the moment of inertia of the body must be determined using triple integration, because there you will have integral I will now be so the integration process can, however, be simplified to a simple single integration, provided the chosen volume element has differential size or thickness in only one direction. So shell or disk elements are often used for this purpose of investigation. In order to obtain the moment of inertia by integration, consider only symmetric bodies having volumes which are generated by revolving a curve about an axis. An example of such a body is shown here in figure A. We have a curve. This is the curve. So it's now rotated around the y-axis to form this volume. So two types of differential elements can be chosen. Number one, shell. Number two, disk. So shell element. If a shell element have a height h, this is the height h, and radius r equals to y, which of course will be equal to x, and then the thickness, the y, is chosen for integration. So this is the thickness, this is the y here. So then the volume, the v, will be 2 pi y z dy. 2 pi y is the circumference, because we have already said that radius is equal to y. And you know that circumference is equal to 2 pi r. And then if r is equal to y, then it should now be 2 pi y. So, and then since it's a volume, it has 3 dimensions, which is x, y, and z. And here you have circumference, then with the thickness, and then the side that is growing. So this element may be used in equation 2 or 3 for determining the moment of inertia, Iz, that is about z-axis of the body, about the z-axis, since the entire element, due to its thickness, lies in the same perpendicular distance r is equal to y. So from z-axis, now looking at disk element, if a disk element having a radius y and a thickness dz is chosen for integration, as shown here in figure C, then the volume will be pi r squared dz. That is pi y squared, because r is equal to y. That's the area of this times the thickness, forming a volume or a cylinder. This element is finite in the radial direction, and consequently, its paths do not all lie in the same radial distance r from the z-axis. So as a result, we cannot use equation 2 or 3 to determine Iz directly. So instead, to perform the integration, it is necessary first to determine the moment of inertia of the element about axis z, is about this axis z, and then integrate this result. Parallel axis theorem. If the moment of inertia of a body about an axis passing through the body's mass center is known, then the moment of inertia about any other parallel axis can be determined by using the parallel axis theorem. So this theorem can be derived by considering the body shown in the figure, this body. So let's just look at the body from here, which is the center of mass, G. Then we have a body, dm, at a distance r from the center of mass. And then we know that from geometry, this is x prime, this is y prime, and this is r prime. Then r prime will be equal to, r prime square will be equal to x prime square plus y prime square. So if now this point is now moved back here, or we are looking at the point from here, so we now look at r from this point to this point, from A to dm is now what we call r. Then the side here will now be from A to this point. which is d plus x prime. And then this is the y aspect of the r. So we now have that r square is y prime square plus d plus x prime square. So hence, the z prime axis passes through the mass center, whereas the corresponding parallel axis, z axis lies at a distance, constant distance d away. So this parallel axis at a distance d away. So selecting the differential element of mass dm, this, which is located at the point x prime, y prime, and using the Pythagorean theorem, r square is equal to this plus this. That is this plus this square plus this square. We can express the moment of inertia of the body about the z axis as I is equal to integral r squared dm, which we already know. Then our r squared now is d plus x prime square plus y prime square. So, which we now give this when we open up d plus x prime square. And then we collate, which is still the same. Then r prime square is equal to x prime square plus y prime square. R square is equal to x square plus y square. So r prime square is equal to x prime square plus y prime square. And this two, that is this, can be replaced with this. They are the same. So the first integral represents the moment of inertia about this mass center, IG. The second integral equals to 0. This is equal to 0. This is IG, while this one is 0. Since the Z prime axis passes through the body's mass center, and then integral x prime dm is equal to xm, because that's the center of the mass, which is equal to 0. So, and then this one 0 times 2d will give you 0. So finally, the third integral represents the total mass of the body. Integral dm is mass, then times d square. So hence the moment of inertia about the z axis can be written as I is equal to ig plus md square, because this d square is still remaining there. So where ig is the moment of inertia about the z prime axis passing through the mass center, m is the mass of the body, and d is the perpendicular distance between the parallel axis z and z prime. So radius of gyration. The moment of inertia of a body about a specified axis is radius of gyration, k. This is a geometrical property which has unit of length, that is meters. When it and the body's mass are known, the body's moment of inertia is determined from the equation I is equal to mk square, or k is equal to integral, I over m, square root of I over m. Note the similarity between the definition of k in this formula and r in the equation, the I is equal to r squared dm, which defines the moment of inertia of an elemental mass dm of the body about an axis. before we now integrate. Composite bodies. If a body consists of a number of simple shapes, such as discs, spheres, and rods, the moment of inertia of the body about any axis can be determined by adding algebraically the moment of inertia of all the composite shapes computed about the axis. Algebraic addition is necessary since a composite part must be considered as a negative quantity if it has already been counted as a piece of another part. That is, when you have a body protruding into another body, or when you have a slot, that is a hole, then you have to look at them as negative. So, for example, a hole is subtracted from a solid plate. The parallel axis theorem is needed for the calculation if the center of mass of each composite part does not lie on the axis. For the calculation, then, I is equal to Ig plus Md square. Here, Ig for each of the composite parts is determined by integration for simple shapes, such as rod and disc, and it can be found from a table. Thank you. End of part A. Do not forget to like my videos, to subscribe to my videos, to share my videos, then press the notification bell if you have not done that for new videos. And then if you have not registered as one of my, if you are one of my undergraduate students and you have not registered, so you have not subscribed to my channel, please do so with your real name. Thank you, and God bless you.